right, I am going to, I'm going to invite Craig Wolf up for our next presentation, our water quality report card, looking at long-term trends. Okay, so you'll hear, and you've heard a lot on relationships and partnerships. This is one 25 years in the making. The district with Denver, Aurora, and Lakewood, together what we call the JTF, partners every year for wet weather in-stream monitoring as a phase 1 permit requirement to the state. We're presenting 20 years of data from this effort today, 541 composite samples from the same 5 sites taken year after year when the rain gauges detect rain and the stream gauges indicate a rise. So we're interested in both the quality, the concentration, and also the total stormwater load. So we look at both with the addition of changes in hydrology as part of that. So here are those 5 sites. We have 3 along South Platte River, 1 on Tollgate Creek, which flows into Sand Creek, and 1 on Sand Creek prior to its confluence with the South Platte River. So here's our upstream South Platte River site at Inglewood Water Treatment Facility at Union Boulevard, what we call our downtown South Platte River site below Confluence Park at Commons Park or 19th Avenue. And then Tollgate Creek at 6th Avenue Bridge, coming into Sand Creek at the Burlington Ditch siphon structure. And then our most downstream site on the South Platte River, which is upstream of Henderson Road. And with that, I will hand it over to Craig to detail the analysis.
Good morning, everyone. I was happy to see that Brick introduced you to some data slides before I'm up here. So I would appreciate if everyone take a drink of their caffeinated beverage so we can get through this presentation here, because you're probably going to see some more box plots, or I guarantee you, you will. So I'm not going to go into the details of our stormwater monitoring program, with the exception of just going through a storm flow here. We typically see a 2 to 3 day rainfall event in Sand Creek, and this is a hydrograph from Sand Creek. It's noted by the 2 ends, the X's on each end, when that storm duration occurs on there. We have automated samplers that collect a composite sample, and in this case here, we see 2 days were collected in that shaded area. And then we identify what is the base flow conditions and what are storm flow conditions in there. We subtract the base load from that total discharge load, and we arrive at the storm load. Our analysis looked at trends. We used the seasonal Kendall trend analysis approach. It really likes that approach groups data, and it looks at the same groups of data over time. In this case, we had 20 years of data. And that analysis looks for consistent trends among all the groups. In this case, for water quality and loads, we group the data by spring, summer, and fall. We really don't want to compare a spring storm event to a late fall event, or vice versa. So that's when we look at just the spring data all at the same time. That analysis compares all the trends and sees if there's a significant difference from a slope of 0 or a negative slope or an increasing slope on there. For our flow analysis, we looked at monthly data rather than grouping it into the seasons. And then we also looked at 4 concentrations: total suspended solids, total phosphorus, total nitrogen, and then conductivity on there. And today I'm just going to present the solids data and the phosphorus data. And I'll get into the dirt of everything here. This is the 20 years of suspended solids data for all sites on there. From upstream, there at Union, that median load median concentration, I should say, on suspended solids is right about 200 milligrams per liter. All the way downstream at the Henderson site, downstream of Denver, that median concentration is 250 milligrams per liter. So not a big change over a long distance and a big influence. We look at Tollgate Creek. That's where we see a high variability in there. Concentrations around 400, and then increasing that 90th percentile up there at the top of that whisker is about 1,400 milligrams per liter on there. When we look at the data on an annual basis, and I'll just plot all these annual figures here, you're going to see quite a few of these coming up here, and I'll get through them quickly. This is 20 years of data, and I'm not really interested in you trying to figure out what is that concentration up there, how much is it, how many years there. There's 20 years of data right there. What I want you to focus on is the whiskers. That 90th percentile whisker and the top of the 75th percentile, which is the top of the box. And my little take-home message for everyone today is that less is more. Less concentration in the river is less variability, and that leads to more management in the river from stormwater. More management is going to drive that concentration down even further. 20 years of data, you'll see general patterns in there. That upstream pattern up at the top left, bottom right is downtown. And you can see that decreasing pattern over time. When you get into the tributaries, Tollgate Creek is the top left, Sand Creek is bottom right there. We see a little more variability in Tollgate Creek. Sand Creek, we see a significant decreasing trend over time on here in terms of concentration, right there. We're looking at that pattern. How does that trend change over time? So in Sand Creek, we've seen a decreasing trend in concentration for suspended solids. When we get all the way downtown, or downstream of downtown area, all the way at the end of our monitoring stations there, we also see a significant decreasing trend in total suspended solids concentrations on here. This trend here and the one with Sand Creek was roughly 15 milligrams per liter of suspended solids. That's a decrease per year over the 20-year period on there. Jumping into the 20 years of phosphorus data, you'll see the concentration upstream there. That median concentration is 0.3 milligrams per liter. All the way down at the downstream end at Henderson, that concentration is 1 milligram per liter. In the middle there at Tollgate Creek, it's about 0.4 is the median, and then you get up to a high in the variability of about 1.7 milligrams per liter of phosphorus in the system. So we see a little more variability in the smaller channels, a little more erosive nature in there. And just for my public service announcement on phosphorus-free fertilizers, no P, please, on there. In terms of the annual pattern in there, the upstream station at Union, we see relatively stable concentrations of phosphorus over time. We haven't seen any trend there. When we go downtown, you see that decreasing trend pop in there. That's a decreasing trend of about 7 micrograms per liter of phosphorus over time. And so that's decreasing on a per year basis over 20 years. That's a significant decrease in concentrations on there. Less concentrations are more. When we get into Tollgate, that flashy nature of the system, you see more solids, you see more phosphorus in the system, more variability. It's up and down. That 90th percentile on each year is highly variable. When you get into Sand Creek, that 90th percentile concentration is relatively narrow. That range is narrow. We don't see the extremes in Sand Creek that we see in Tollgate. Again, in Sand Creek, we don't see a decreasing trend. We see a decreasing trend there, but is that significant? No, it's not in terms of our analysis. When we head on down to the downstream station at Henderson, we see a significant decreasing trend in total phosphorus concentrations. This trend here is similar to the upstream trend at the downtown station. So on the South Platte River, we see two decreasing trends in total phosphorus concentrations, one at downtown, one at Henderson on there. And just to summarize those trends, the green arrows pointing downward are significant decreasing trends. The red arrows pointing upwards are significant increasing trends. We see two decreasing trends in total suspended solids in the river, and we see it in phosphorus as well. They're generally linked. Suspended solids and phosphorus go hand in hand in stormwater. The important part out of this right here, and I'm sure Holly will get into the report card analysis, is that we see a decreasing trend at the downstream station in total suspended solids, in total phosphorus, and total nitrogen. The one increasing trend that we see is in conductivity, and that's largely tied to the de-icing of many of the roads over time on there. This is pretty common along the Front Range. We looked at the seasonal hydrology. We only looked at the April to October data. In Sand Creek, this is the only station that showed a decreasing trend in time with hydrology. It equates to roughly 7 CFS per year over time in a reduction. That pattern right there is probably largely tied to the development of the Central Park communities, Westerly Creek, and that increased bank storage capacity in Sand Creek to hold, capture that storm event, slowly release it over time so you don't have that high peaking flows through that system. When we get into the load analysis, I like this image here of Sand Creek. It's right at the Burlington Ditch. This is the 2013 flood, and you'll probably hear a little more about it later on today. And I'd like to get into the 20 years of load data, suspended solids data for this analysis that we looked at. At the upstream station, the TSS load is right about 100,000 pounds on an average storm event. When we go downstream all the way to Henderson, that average load in there is about 900,000 pounds. We see the variability can reach up to 8 million pounds of suspended solids in a storm event on there. Again, we see the increasing trend for the low data coming up from downtown into the Henderson site on there. We see relatively low loads in Tollgate, and there again in Sand Creek. These four figures here, top left, I just want to go through is upstream, downtown, top right on there. Then we get into Sand Creek, and then Henderson site. The only load that we saw a decreasing trend is at Sand Creek. Part of this is due to the flood in 2013. When you look at that lower left figure up there, the last 6 years represent the post-2013 flood event, where the high flushing event removed much of the suspended solid loads in that system, and we see this carry out through all the years in monitoring since on there. This also ties into the phosphorus concentrations we see in Sand Creek, because they're relatively low compared to all the other stations in there. This 20 years of data for all the sites again. That typical phosphorus load upstream is about 150 pounds per storm event. When you get downstream to Henderson, the typical storm event has about 3,400 pounds of phosphorus in it. That peak can get up to about 14,000 pounds in a storm event in there. So we see an increasing trend in the load, suspended solids load going through town. We see an increasing trend in the phosphorus load going through town, but the key is on the concentrations when we get into it. This panel right here again touches on the 4 stations. That lower left station there is a significant decreasing trend in total phosphorus loads for the whole system for Sand Creek. Again, it highlights that post-year 2013 flood event and the influence on the trend analysis itself. When we get into the other figures, you can see that decreasing variability, the decreasing concentration in loads through the system, and that's all tied into the stream management and the benefits of stormwater management. And for the last part here, I'll let Holly give you the report card.
So if this is our report card, how did we do? The upward trends in specific conductance, which we believe are due to road salting, are very difficult to treat. If we're concerned about nutrients, which we very much are concerned, the downward trends in concentration of nutrients and the downward trend in loading of TSS and phosphorus look really great. And the other thing that we need to consider is that during this 20 years of data, how much more impervious area have we created? That white boundary is the district boundary. And that difference flashing shows new impervious areas and intensity of those areas. So while we've been building and paving, we've also made some really good decisions on how to manage those areas. To sweep streets, to stabilize streams, to construct SEMs, to talk about phosphorus-free fertilizer campaigns. Let's keep talking about that one. And that's just to name a few of the things that we all do, all of us in this room. So thank you truly to everyone in this room, because we all play a role in these decisions, and we're making decisions every day that impact the quality of water in our region. Thank you.